Morning. Yeah, there we go. Welcome to Windows Azure Internals. My name is Mark Krasinovich. So for the next 75 minutes, I'm going to give you a little tour behind the scenes of Windows Azure. I'll start with talking about the data center architecture, show you a little bit behind the software architecture that runs our data center, talk a little bit about the hardware architecture that makes up our data center. Then I'll talk about deploying services. So this is something that many of you have done. I'm guessing how many people have deployed a service in Windows Azure? So yeah, it looks like about 3/4 of you, which is good. So I'll talk about what happens behind the scenes when you deploy a service, all the way down to your service instances, your roles, getting started on a VM on top of a server. Then, of course, we introduced a couple weeks ago Windows Azure Virtual Machines or Infrastructure as a Service. So I'll take you a little inside of Infrastructure as a Service and talk about how those are configured differently than the Platform as a Service web and worker roles on a server, how they use disks differently, how their disk layouts are different, and I'll give you some tips on maximizing disk performance on virtual machines. Speaking of tips, I have a number of tips sprinkled through here, so I wanted to make this not just an interesting behind the scenes, what's going on, just out of a cool geekiness factor perspective, but also tell you how give you a few tips on how you can use that internals information to your benefit to maximize your usage of Azure. Then I'll talk about maintaining service health. So this is the way the platform helps your services stay up. What happens when a server fails? What happens when your role crashes? What steps does that platform take to fix that? And then I'm going to conclude with a tour of, or an overview of what happened on February 29th of this year. How many people were aware that we had an incident? So quite a few of you are. How many people were impacted by that incident? So I apologize to you for being impacted. And this section right here at the end of it, I think, really demonstrates philosophy that we've adopted in Azure, which if you look at the other cloud providers, we're, I think, different in this perspective, is that we want to be open about what we're doing. This is why I'm taking you underneath to show you what we're doing, including talking about places where we made mistakes, like what happened on Leap Day. I'll take you through the timeline of what happened on Leap Day, and it's going to reinforce a lot of the concepts that I'm going to explain about the way Azure works at the beginning of the talk. So I think it's a nice bringing together of the rest of the talk, and plus it shows you what happened, and I'll talk about what we learned about what happened as well. So first, let's talk about the data center architecture. Now, that's not really a server in Azure. That's really in my basement. That's the server that my daughter runs for me. So I'm training. No, actually, it's not. This is a server in our test cluster. We've got in a building on Microsoft's campus, we've got a bunch of racks where we can go and do kind of mini testing of Azure services, and that's an example of one. The data centers that we've got are actually much more clean and much more sophisticated. The wiring is a lot more robust. Here, it's kind of test, so it's still, I mean, but you can see it's kind of clean still. You can see that bundle of wires there in the middle. Does anybody know what that is? What piece of equipment that is? Right here. Yeah, that's the router. You know what its name is? What that piece of equipment's called? The top of rack router. And but it's actually in the middle of the rack. That's because most network administrators are pretty short. So let's take a step back and talk about what data centers we've got. We've got 8 locations now. We just opened 2 in the last few months. You can see that these circles here on this world globe represent Microsoft data centers in general, whether they're running Azure or other properties like Hotmail or Bing. The ones that are highlighted in yellow are the ones running Windows Azure. So you can see there's 4 in the US, there's 2 in Europe. In fact, there's one very near to where we're standing right now, that one that we call Western Europe. Then we've got 2 over in Asia as well. And we're actually, the total number of server count that we're up to is in the hundreds of thousands at this point. We're growing at an amazing pace. I don't know if you noticed, but a couple weeks ago, or no, about a month ago, we closed or capped the San Antonio data center, which is sitting there in the middle of the US south, meaning that new subscriptions can't deploy services to that data center. And that's because it actually filled up And so if you've got an existing subscription, if you already made a subscription, you can deploy services there, but new subscriptions can't go there. And we're imminently going to cap Chicago as well, which is up there at the top, because this is kind of a bad problem to have, but yet a better problem to have than the reverse, and that is the demand has been absolutely phenomenal over the last few months. It's exceeded our expectations, and anybody that's built out data centers know it takes a while to build them out. So we've got N number of data centers right now under construction that will be opening up over the next 6 months. In fact, we expect probably to double our capacity over the next year. And I think at the keynote, Brad said that the total amount of Azure compute we've got is bigger than the whole world's compute was in 1999. When you take a look inside of a data center, there's a software component. It's called the Fabric Controller, and this is the heart of what is kind of the data center operating system. We talked in the keynote about cloud operating system. That's really kind of Windows Server. But the data center operating system here is really the Fabric Controller. And I consider this the equivalent of an operating system for a single machine. And if you look at what a single machine does, an operating system does, it manages hardware resources, it provisions the hardware resources, it virtualizes them, and it manages the lifecycle of applications or processes and windows on them. And the Fabric Controller does the same thing, just at data center scale. So it's responsible for looking at the hardware that it's got under its control, provisioning it, meaning getting it ready to do things with it, then deploying applications to it, and then managing the lifecycle of those applications. Your worker roles. How do you update those worker roles? The Fabric Controller is doing it. How do you stop your service? The Fabric Controller does those things. How does it monitor the health of your service? So it's got a health model, kind of primitive at this point. We're going to be evolving it, but that's another role of the Fabric Controller. And the inputs then are something that describes the hardware that it's going to manage. And this, I've got actually a copy of a file that we feed into the Fabric Controller to tell it what it's supposed to manage. This is the datacenter.xml file for one of our test data centers we've got, CO2. And if we go scrolling through here, you can see there's things like the IP addresses of routers. And oops, something's going on with my display here. Sorry. It's not scrolling the way that it should be. Hold on. And my wheel mouse isn't working, apparently. But let me scroll down here, and you can see we've got machine pools with certificates that we've got that authenticate them. And down here are actually where the racks are all described, including the NICs IDs, the asset ID, the blade ID, and each machine has got an IP address as well as a node ID you can see here. This is the blade ID. So this is really the inputs to the Fabric Controller. With this topology, it understands exactly what it's supposed to be configuring and managing and bootstrapping and provisioning. The data center we divide into what we call clusters. And there's actually a separate Fabric Controller for each cluster of machines. Right now, our cluster size is about 1,000 machines. So it's about 20 racks of 44 servers in each rack. And it varies depending on which data center you're talking about and what kind of hardware is in that data center. But that's roughly it. The reason that we divide the data center into these clusters and give Fabric Controllers autonomous control over their own cluster is a principle that we follow in Azure and that you need to follow with any time you build a large-scale distributed system, and that is fault isolation and containment. So if there was a Fabric Controller that went haywire, it's going to impact just its cluster. I mean, that's not a good thing that it impacts its cluster. The customers that are running in that cluster don't like it, but it's better than everybody in the whole world across all data centers being impacted. And so that's kind of the benefits of fault isolation. And we try to follow that fault isolation philosophy everywhere we can in Windows Azure. I'm going to introduce you to a little tool, command line tool that we used to perform manual operations on a Fabric Controller. And again, I'm going to be talking to our test data center. This is the one that I was just showing you. It's data center.xml. I'm connected to the Fabric Controller front end, so it's got a REST API on the front of it using a tool called FC Client. This is a kind of troubleshooting diagnostics tool we use. And if I type get nodes, this lists out the blade IDs of all the nodes that this particular Fabric Controller is responsible for. Now this, and their states. So you can see we got a summary here at the bottom. Tells us that there's 367 nodes in the ready state. This is a smaller than normal cluster because it's test. There's 22 in what's called a state called human investigate that I'll explain a little bit later. One's out for repair, meaning we had to pull the blade, send it back to the manufacturer because it's got a hardware problem. And so this is just one of the commands. I'm going to be showing you some other ones with that tool to demonstrate some of these concepts of how the Fabric Controller operates. So inside of a cluster with the Fabric Controller's software topology, if you've written a Windows Server application, you know that you divide your application into roles, and then your roles, you scale them out. There's stateless roles, web and worker roles. And you scale them out for a couple reasons. One's availability and one's scale out for capacity. For the Fabric Controller, we also follow the same principle. Now, the Fabric Controller is a little bit different than a standard Windows Azure service, though, because it's what we call a stateful application. It's a lot easier to write a stateless application, one where requests come in, you process those requests, and then you dump the output back into a SQL database or Windows Azure storage. Because if one of those instances fails in the middle of its operation, that's okay. You just have the client restart it, or you pick up the work item and start it again. But the Fabric Controller keeps state about what's going on inside the cluster, the hardware state and the state of the services deployed there. So it's not going to actually stick that state over in SQL Azure. It's going to maintain it itself. So it's a stateful service that replicates state across instances. We've got 5 instances of the Fabric Controller. One of them is called the primary, and it uses a Paxos ring to maintain quorum of decisions. So when a state change is about to be made, for example, we're going to deploy a service to a particular server, then the primary sends that command, that update, to the replicas. And when it gets back a response from a quorum, which would mean at least 2 others say, yeah, I got that, then it can go ahead and proceed with that state change, knowing that if there was any failure, we still got a consistent view of what's going on. And the reason that there's 5 is for really high availability under unusual circumstances, because when you talk about hundreds of thousands of machines, there's unusual circumstances every day, every hour of every day, ones that most people running their own machines never encounter in the lifetime of those machines. We run into these things all the time. So the reason we got 5 is that we can be updating the Fabric Controller, meaning that one of the instances is down, is rebooting to pick up the changes. So that means we're down to 4 instances that are available, and then there's a hardware failure on one of those 4. So that means we'll still have 3 ready. We can maintain quorum and continue operating. If we drop below quorum, we move into read-only mode until we're back at quorum. So this keeps us in operations under those kind of double kind of faults. If you take a look at our kind of network architecture, so of course we got racks like you saw. We've got top-of-rack routers. This is a comparison between the old network that we started with 3 years ago and the new network that we've got now in place in Windows Azure. So in the last 3 years, we've done a network upgrade across our data centers. And if you look at this topology on the left, it's kind of your traditional tiered network architecture. We inherited this actually from the Bing guys. This is the kind of architecture that they were using. This architecture is decent for north-south traffic or coming from the blades out to the internet for things like web search. It's really not good for what we call east-west traffic, meaning one blade over on the left side of the data center wants to talk to one blade over on the far right side of the data center, because if you look at this topology, how many hops does that request have to take to get to that other server? It has to go all the way up to the DC router and back down through 2 mid-level routers plus the top-of-rack router, and each one of those points becomes narrow and narrow in terms of bandwidth. In fact, the total east-west bandwidth from one end of that data center to the other in that topology is about 120 gigabits. This architecture on the right, this new one, which we're really pretty proud of, we call it the Quantum 10, or it's a clause architecture, fully bisected graph. Every server has a direct path to every other server in the data center. that's not overloaded. There's no oversubscription on that path between servers. So this means for Windows Azure, where you've got one server over here talking to storage over here, then we don't run into that oversubscription problem that we have on the left. And the total amount of east-west bandwidth that we've got in this architecture, get ready for it, a little bit of an improvement. So that is kind of one of the benefits that we're seeing now of having that in place. One of the changes we've also made in our network architecture is that we've gone from a hardware load balancer to a software load balancer. And the software load balancer gives us much more flexibility than the hardware load balancers we were using, plus it's much cheaper than a hardware load balancer. Hardware load balancers cost on the order of $25,000 to $50,000 a piece, and we always have to buy 2 of them every place we put them because we need redundancy. But they've got lots of limitations. They've got fixed size buffers, which means, and they've got fixed size ACL lists. So when we ACL to create these VLANs inside of our data center, we start to push the limits of these hardware routers. So we needed to get off those, go to a more flexible, cheaper, scale-out model, and we built the software load balancer. It's built using the same service model that your Windows Azure applications use. And we get the scale-out. Now, how much overhead does the load balancer add? Let's go take a look, because this is an important question. If you're going to talk between servers in your application, I don't know what's going on with my mouse. But let me connect to 2 machines, and what I'm going to do is a ping test between them, one through the load balancer and one directly between the dips. Let me explain a little bit more what I mean there. These 2 VMs, these are IaaS VMs, are sitting inside of the same cloud service. If you saw my talk a couple days ago on virtual machines and cloud services, you know that a cloud service is kind of a private network. The VMs in it have what are called dynamic IP addresses, or DIPs, assigned to them. They're from the 10 space of our data center. You saw those 10 dot addresses in that data center.xml. So each server has a 10 dot address. Now this cloud service also has a public IP address, because every cloud service gets a public IP address. So this is VM2. Let's move that over here. And VM1. Let's move that over here. So this has a 10 dot address. If we do an IP config, you can see this is 10.119.118.7. And this is 10.119.116. I'm going to run a little tool called Latte that we've made to measure network overhead. And the first thing I'm going to do is, if you look at this command, this is the Latte client, which means it's going to send commands to the other side, to that 10.118.7 address, to port 1000. The message size is 1,000 bytes, and it's going to do 10,000 iterations of that send. And then it's going to print us the average latency of that command. And this guy over here is just going to sit here as a server responding to those. So I'm going to press enter. And in a second or two, we're going to get a spit out of the average latency going from one machine to another inside of the same virtual network. And you can see that the latency, it's about 500 milliseconds. This is the kind of latency you get between servers inside the same cloud service. And when I talked about virtual networks, where you can connect cloud services together inside the virtual network, it's the same kind of latency you'll get between those when you go from dip to dip. Now, how about going through the load balancer? Let's run that test again. And something kind of interesting I want to highlight here. Notice that the target port here is 500 on that public IP address. This public IP address is mapped to that dynamic IP address there over there on the other server. It's also doing a port mapping from 500 to 1000, because this guy's listening over here on port 1000. And if we go to the portal, you can see where that mapping takes place. Here, if I go to endpoints, you can see public port 500 maps to private port 1000 on HTTP port 80. So the software load balancer is also doing port mapping as well. And let's fire that up. And in another couple seconds, we're going to see the overhead of the load balancer. And the overhead is, it's about 500 milliseconds. So this is what you're going to see going through the load balancer, about a 500 millisecond overhead. This is the software load balancer's overhead. We've also measured, of course, the hardware load balancer's overheads. And if anybody knows what hardware load balancer overheads are, it's about 500 milliseconds. So we didn't regress, which is an important thing for us, switching these architectures and getting the flexibility we did. So that's a tip there on maximizing your network performance by skipping the load balancer if you can, so you can save that half a millisecond. Very important, that half a millisecond. So let's talk about provisioning a node now. So this is, when we're going to deploy a service, we need to have servers ready to deploy those services onto. And this, if anybody's got an automated kind of data center management infrastructure, you probably have something similar to what we have going on here. There's a node here. There's the fabric controller up there, and let me explain what you see in the fabric controller. It's got what's called an image repository in it. This is where the OS images are stored. So every OS image we've got in our live catalog, you can go to the portal, for example, and say that you want to be bound to a particular version of Windows from a few months ago. All of those images are stored in the fabric controller, including what we run on the host OS as well. We also, that's the Windows Azure OS right there. We also have a maintenance OS. That maintenance OS is used for the first time boot of the node. And then we've got images for the roles. So these are your own images for your applications. And then you can see there's a deployment server there, and there's a Pixie server there. So we're using off-the-shelf Windows technology to manage the data center. The blade gets powered on. One of the things, if in that data center XML, if we looked through the whole thing, you would have seen IP addresses for what we call PDUs, or power distribution units, which feed into each rack and let us control the power remotely on each server. So what the fabric controller does is hit the PDU to power on the node, and when the node boots, it's configured to Pixie boot, and the Pixie server on the fabric controller responds to the Pixie boot and deploys the maintenance operating system, which is actually Windows PE. Same thing that many of you have used to deploy Windows images or fix broken Windows systems. And Maintenance OS formats the operating system and then pulls down, using Windows deployment services, the host operating system. It's a VHD, so Windows Azure uses boot from VHD. It used it actually before that became a feature in Windows 7 and Server 2008 R2. It's one of the kind of technology back and forths we've got between Server and Azure, where things can flow in either direction. And at that point, we have to use sysprep, everybody's favorite command in Windows, sysprep. And then the machine boots, and the Fabric agent connects with the Fabric controller. So there's a little agent, kind of emissary of the Fabric controller to perform its bidding remotely. And now the server is ready to start accepting applications. It's part of the machine pool now. When you go to the portal, or when you go to deploy a service, there's a few ways you can do it. And this slide kind of shows you the flow of those ways. You take your service, one way is through the portal, another way is through app controller, like you saw me do the other day. Another way is through PowerShell. Now this is the flow. The service package gets given to app controller gives it, or the portal, and it's handed off to service called RDFE. I'm sure some of you in here have been to previous sessions or read documentation and know what RDFE stands for. Does anybody know what RDFE stands for? Red Dog Front End, right. Somebody's got Red Dog Front End. Red Dog Front End was the original code name to Windows Azure, so a little trivia on the history of Windows Azure. Windows Azure was started by a group of people that, many of whom came from Windows, including one of my heroes, Dave Cutler, who I kind of followed along in his footsteps. I actually was in Windows, and then he moved to Azure, and then I moved to Azure. And he was part of that original group that started the project. He came up with the code name, Red Dog. And there's a little kind of interesting story here, which I still haven't gotten to the bottom of yet, which is he was driving, the team was down in Silicon Valley, and they were driving around looking, they were checking out the Hotmail data center down there because they wanted to see what data center operations look like so they could figure out what the Fabric controller and Azure needed to do to optimize that. And they were saying, hey, we need to come up with a code name. So they were in the car driving, need to come up with a code name. and they tell me that they passed a place called the Pink Poodle. They say they passed it. They say they didn't stop there. They vehemently deny that. And Dave Cutler really liked, I guess, the poodle and said, let's call it the Pink Poodle Project. And, of course, everybody else in the car said, you know, are you out of your mind? We can't call it the Pink Poodle. And so somebody said, oh, how about Red Dog? So that's, the name is Red Dog. Now, I haven't been able to find out what the Pink Poodle is, what kind of establishment it is. And I can't get anybody to admit they've been there either. So if you find out, let me know. And let me know if it's worth going. So RDFE sends the service to the Fabric controller. Now, the Fabric controller that it sends it to, remember I've got lots of Fabric controllers in each data center even. So which one does it send it to? Let's talk about that. Well, first, RDFE is the front end. I mentioned it's what receives the service package, picks the Fabric controller. It's got some other responsibilities too. It does billing, metering. It does what your account sign on. So when you log in, you're logging into really the RDFE. You're also, the management surface is all exposed up through RDFE. But the place that it picks which Fabric controller depends on what you've told it as far as constraints. So one of the things you can do when you go to the portal and deploy your service or the management APIs is say, I want to go to this region, like North Central US. Well, you can't do that really anymore if you're new. But how about East US? And that dictates which data center or data centers RDFE can pick to deploy to. If you've gotten a little more narrow, let's say that you've said, you've created what's called an affinity group, and you've got a service already deployed into an affinity group, say AG1. And then you say, deploy this service into the same affinity group. Well, service in that affinity group AG1 has locked where AG1 is, which data center it's in. So when you deploy your second service into AG1, it's going to go right to that same data center. And that means that you're not going to be paying data center, transfer charges going out to the internet for traffic between those two services. So that's the benefit of the affinity groups. But when there's a choice, when RDFE gets to say, which cluster should I pick because the person just picked this data center, which one does it pick? It depends on the load of the clusters. It tries to even out the load across the clusters. And as a really deep inside internal tip, I'm going to show you the algorithm. That's right, that's it. So it should be fairly obvious what's going on there. That it makes the best choice absolutely possible. Now, when you talk about Fabric controller deployment steps for a particular service, there's a few things that happen. The first is the processing of the service model files. If you've built an application in Windows Azure, you might have come across the service model files. And you've interacted with them for sure indirectly as you've created your project and you've updated the configuration for your application, for your roles. So I've got Visual Studio open to a cloud service project. You can see that I've configured an input endpoint for this, HTTP front end. And then I've got settings here for Windows Azure plugins, like the RDP plugin. And then I've got other configuration, like an instance count. When I modify this configuration, I'm actually modifying underneath the hood this file right here, CSCFG. And if I take a look closer at this, this has the configuration for each role that's part of my service. This is a 2-role service. You can see that it's here, there's configuration settings that we just were looking at. Here's the instance count we just saw on that previous page. Here's the instance count for worker role. And when I go back and change this to 3, I'm actually changing that file. So that's the configuration file. And then there's the service definition, which is the kind of logical structure of the application. It's deployment independent. So you can take this same thing and deploy it multiple places, which I have. I've actually got the same service from this project with configurations to deploy to the staging cluster, to deploy to production, to deploy to Europe. I've got this thing all over the place. And you can see things like startup tasks as part of the structure, the websites and the web role. Here's the input endpoint that we saw configured there, modules, and so on. So these two files, with the code that you've got and the data you've got, or what's torn apart by RDFE, and it figures out what to do with it, or torn apart by the Fabric controller, and it figures out what it needs to do. So, for example, how many VMs did you ask for? What size are those VMs? Which code goes into those VMs? And it prepares your service to get started by handing those artifacts and instructions to the host agents on the servers that it picks to deploy to. There's also network configuration that the Fabric controller does. Of course, it's going to assign dynamic IP addresses to the individual VMs. It's also going to assign a virtual IP address to the whole service. And then it's going to configure the software load balancer to do that mapping that we saw happen a little bit earlier. When it's picking which servers to go to, the Fabric controller, it's not as simple as saying, is there space? Because there's some things that we've got as promises to you. One is that, well, if you've asked for a certain amount of CPU, a certain amount of memory, and so on, of course, the VM, we've got to be able to have a server that fits that VM. But also there's a promise we make to you about availability called fault domains, which I'll talk a little bit more about later. We've got to honor that. And then we've got our own soft constraints. We'd like to pack VMs. In fact, we'd like to pack your roles that are part of the same update domain, instances from different roles that are part of the same update domain on the same servers, which gives you good locality and makes our updating of the data center faster. Once we've picked out which servers to go to, we deploy. So this is kind of just a simple animation where I've got a service with 2 roles. You can see the front end has a count of 3 instances of large VMs, which are 4 cores. And the back end has a count of 2 with medium VMs, which is a 2-core VM. This is demonstrating with 8-core servers. And so what the Fabric controller is going to do is find places on servers to hold those 4-core VMs. It's going to try to spread them out across racks, at least 2 racks, according to fault domains. Again, I'll explain a little bit later. And then it's going to try to pack the back ends with the front ends. Then it's going to wire up the software load balancer to map the VIP, mycloudapp.net, to those DIPs, and we're ready to go. Let me show you a tool that we got to manage our data centers, and it's called the Fabric Viewer to kind of troubleshoot. So this is a diagnostic tool. And this is that test cluster, the same one we saw the data center XML for. And what this is showing, and these are 8-core servers in this test cluster. So you can see each one of these tiny boxes represents a VM, these green boxes. The size of the box represents how many cores it's taking up. The red indicates servers that are bad. And what we can do with this tool is find a particular cloud service and highlight it. This is my branding police app, the same one we were looking at the source code to. I've deployed it into that stage cluster, and I can get its deployment ID. So if a customer has a problem, we'll say, hey, what's your deployment ID? There it is. And then we can use tools like Fabric Viewer to go see what's going on with it. So if I enter that in here, you can see highlighted in yellow is branding police. And I click on it. As soon as the internet helps me, click on it. So I've clicked on it. And you'll have to trust me that I clicked on it. OK, so let me see if I can hit the front end of it to prove to you it's branding police. And there we go. There it is. So that's my little application. You can see that it's across 2 servers. We got 2 instances of the web role, 2 instances of the worker role. What does that tell you about these 2? There's something we know just because of what I've told you about fault domains, and that is that one of those is a worker role and one of those is a web role. And then over here, one of those is a worker role and one of those is a web role. But we exactly see that packing that I talked about. Now, what happens more deeply when we're creating the VM? We create a few VHDs. We put the role file into, create a VHD out of that, and then we boot the container. And the load balancer only starts feeding inputs or feeding requests into the services until the role comes up and says, I'm ready. So there's a role entry point. You respond to that with ready, and then the load balancer will start forwarding requests. When you look at inside of a node, it looks very much like Hyper-V, actually. This is a physical node with the host partition. The Fabric Controller agent that I mentioned is there. You can see with each VM inside of it, there's a guest agent, there's your role, and then there's your code and data that's sitting there on the VMs in that role. The Fabric Controller primary is talking to the host agent to do health updates on it, also to push commands into those VMs. And there's an image repository, too, on each server. And this, let me show you the image repository of a particular blade. So I can do get tenant nodes, and this will tell me which nodes that branding police is on by their blade ID, and then I can take one of those and say get node image list, and this will dump all of the images that are on that node, including the various versions of Windows Server, because there's the host OS, like I said. There's also the various versions of Windows Server that the services that are deployed on that server have used in the past. They're cached there. Then you can see that we've got the app VHDs. These are the role VHDs for the active roles that are on that server. And then you can see configuration that's just cached there as well. In fact, if you look here, you'll be able to find my configuration right here. The configuration for the web roles and worker roles, that's my service deployment ID that we saw, that F5. So they're sitting there as well. And then here's the guest agent package. So those are all sitting there. Now, here's a little tip. You want the best performance out of Azure? Make sure you snap to the latest version of the Windows Server, because that's going to be pre-deployed on all of the servers in the data center. If you don't use it and you happen to pick an older version of the operating system and you get deployed to a server that doesn't already have it cached, then you have to wait for that server, that OS image to come down from the Fabric Controller to the server. So that's one way to get maximize performance. Always stay on the latest OS. Inside of a VM, like I said, there's some VHDs that are created, and then they're mounted as disks inside the VM. You can see that there's 3 disks by default on a PAS role. There's a dynamic disk, which is the resource disk, which gets drive letter C. This is your temporary scratch storage. The size of this disk depends on the size of your VM. I think you get 2 terabytes, I think, if you've got an extra large, something like that. Then there's a differencing VHD. Somebody asked me, do we use differencing VHDs? Well, this is one place where we use them, on top of the Windows operating system VHD, as well as on top of your role VHD. Those are differencing VHDs because we want to make it so that when you mess with your OS, you're not messing with the next door neighbor's OS. And so we let you party on your own differencing VHD, and you can actually reset your OS state. There's a reimage instance API. What that does is removes the differencing VHD, respecializes the OS, and then you get a fresh one. So if you've got corruption of some kind, that's one way to reset yourself back to a base state. And we can RDP into a node where you can see, so we'll RDP into 2 of my Branding Police app here. Here's Branding Police and the instances for it. And I'm going to RDP into WebRole 1 and WebRole 2. Actually, we'll RDP into this one over here from this other one. Oh, this is a problem with cached RDP file nonsense. Hold on. And actually, this is a tip for you to work around this RDP file nonsense. Has anybody run into that, by the way? Because I've started running into it lately, so I don't know if the portal's made a change that's causing it. But let me go back and show you how to fix that if you run into it. So the problem is that we saw that username does not exist error. The way to fix that is to save that file to your desktop, actually, which I already have. And then when you've saved it to your desktop, right-click on it, say Edit, and then say Always Ask for Credentials. And that will fix that problem. So we'll TS into one of these eventually. Oh, here we are in one. All right, so here's what disk management looks like. There's that C drive. That's that resource disk. If I say open, you can see that sitting on here are log files. In fact, if you call Microsoft support with the Windows Azure problem, they might ask you to send them the log files in here. This is a guest agent dumping log files, including things like the heartbeats. So how your roller is responding to health heartbeats from the Fabric controller. The paging file is also there. Then the D drive is, of course, Windows. So here's the other one. The reason that it's kind of interesting to show these two side by side is that, I don't know if you caught it, but back here, I say that the role image is either disk E or F. And the reason that you might run into one or the other, in fact, here you can see that the role is drive F. In this other VM, the role is drive E. And the reason that you run into one or the other is when you do an update of your code, what happens is we create a new VM with the new code. Then we shut down your old role, start the new one, and then detach the previous VM. So the drive letters are going to flip back and forth. And then we run my favorite tool, Task Manager, and see a little bit about what's going on here. Here's the guest agent. So there's that agent that's sitting talking to the host. And it's using a REST API here. You can see if I go to the TCP/IP tab, that's the host IP address, another 10 dot address. This is how the guest agent is receiving commands from the host. And then this is your role host. So this is where your DLL gets loaded. And I've got my DLL here. I think it's just called my DLL. Well, it's sort by company name, and then we can find it. And there it is, my webrole.dll loaded inside there. So this is what happens is this host process is the one that's calling your role entry point and doing heartbeats with you. The reason it's separate from the guest agent is so that if you've got a problem here that crashes this, the guest agent will automatically restart it. So I could go and kill this, and after 30 seconds or so, the guest agent's going to say something's screwed up and restart that. Now, here's a tip for you. Keep it small. Keep your packages small. The number of steps, number of copy operations for a service package as you deploy to Windows Azure, for it to get down to a particular server, you can see if you go through the portal, that's one copy up to the portal. The portal then is going to send it to RDFE. RDFE is going to send it to the Fabric controller, and then the Fabric controller is going to send it to the server. 4 steps. So we support service package sizes up to a gig, roughly 650 megabytes per role. And so you don't want to do that if you can. Avoid it. Put your files, the data files, inside of blob storage. So you have one copy operation up to blob storage, and then have your role code go and fetch things as it needs it from blob storage. And so you have at least 2 copies, plus you're only copying what the thing actually needs, not just all 650 gig that it might need eventually. So that, or 650 meg, rather, that it might need eventually. We introduced virtual machines. These operate a little bit differently, and they have to because it's completely different disk architecture underneath. So one thing, there's no standard cached images. There can't be for IaaS VMs because each VM has its own unique personality. It's not like we can have a base OS. And the OSs then are off of OS disks and faulted in using a disk driver, virtual disk driver sitting in the host, off of blob storage. Blob storage has a fixed VHD format for these VHDs. The first time you boot, when you create a new VM from a new image, like you go through the portal experience, you do the sysprep specialize. Gives it a computer name, does your password, and so on. And then from then on, of course, once you've got an instantiated disk, you can just simply boot it. And there's 2 things to note here because there's different behaviors for disks. By default, you just get one disk. It's your OS disk. And that OS disk has a policy on it of read cache and write cache. When you add a data disk, you get a default policy of no caching. So let's stop and take a look at what this topology looks like. I'll actually RDP into one of these. Go to my virtual machine, and this is, and we'll take a look at disk management for this guy and see how it's different than for PAS VM. Now, what I've done with this machine is I've added a number of data disks to it. So we're going to see multiple data disks. We're going to see the OS disk, and we're also going to see the temporary resource disk. Just like the PAS roles get, they get this temporary resource disk, which is where the paging file goes. We don't want to bother with putting the paging file over in blob store when it doesn't need to persist across server problems. When your VM moves from one server to another, it's going to reboot. Don't need the paging file from the previous boot instance, boot session, so we leave it behind on the previous server. And if I run, by the way, there's a little Windows 8 tip for you, Window key X. And now you can see that here's the OS disk. So on PAS VMs, this is drive D. Here it's drive C. Temporary storage here where the paging file is drive D. I've added a data disk here, drive F, and then I've added two more data disks and striped them. And you can see that the data disks and the OS disk are backed by blobs. The default caching policy has the OS disk use a RAM cache as well as a local disk cache as well behind it. Now, the reason why we use different caching policies is to maximize for the kind of workloads that we expect you to be putting on these different disks. With an OS has a relatively small working set that will almost always fit inside of the local disk cache. Unless you're putting an application in there that's got a large data file, the OS fits nicely in the local disk cache, which means that reads and writes almost never have to leave the server. Well, write-throughs go back to the server, but cached writes coming out of the VM just go into the local disk cache and don't go back into blob store. Unless the VM flushes or does a write-through, those will go all the way back through. But in most of the cases, that's not what the OS is doing. So you get great performance for those kinds of workloads. The temporary disk, of course, that's going to be scratch storage, so don't put anything there that you want to keep around. Don't put your SQL database there. That'd be a bad thing. And then the data disk, this is where going directly to blob storage unlocks the potential of many, many spindles. Now, when you talk about the local servers, there's a few disks on the local servers. But when we talk about storage, the servers have dozens of disks on each server. And Windows Azure Storage can split your blob across storage servers. So you can get even more spindles. I think one of the tips I mentioned in the virtual machine talk a couple days ago is if you want to benchmark Windows Azure Storage performance for data disks, run it hot for about 45 minutes, and then Windows Azure Storage will have learned the access pattern, split the blobs, and you'll start to see the maximum performance you'll get. So the tip is, unless it's small, put your application's data on striped data disks. You want to stripe them to even spread across even more spindles over time. Don't put your SQL database, if you care about performance, on your OS disk. So that's the kind of what we've optimized for. And if I go back to that VM, I've got IO meter here, and I've got the data disk and the OS disk here, where I'm going to be hitting with random IOs a very large working set. And we're going to see the difference in caching, the caching policy has, where we're behind a single spindle on the local server for the OS disk cache versus the data disk, which is going back to RDFE, Windows Azure Storage. So let's see what the IOs per second we're getting for the OS disk is. A pretty crappy 50 IOs per second. Not very exciting, is it? Well, let's hope the data disk does a little bit better. Anybody have an idea what we're going to get out of this? Want to guess? 100? 200? How about 2,000? So that's the kind of dramatic difference. And the performance is only going to get better. I mentioned that this is a V1 preview release. We're still making performance optimizations. We're actually making performance optimizations to the local cache and the OS, so that will get better. We're also making performance optimizations to Windows Azure Storage. So even that number is going to get better. But that's where we're at today. Let's talk about updating now. So when you create your service, one of the configuration options you can specify is the number of update domains that it has. By default, if you don't specify, you get 5. And the only way to actually specify this is if you go into your service definition and enter that. Visual Studio doesn't expose this because most people don't care. 5 is enough for small services. What the update domain count does is instruct the platform on what to take down when there's a planned outage. And there's 2 types of planned outages in Windows Azure. One is you're doing the planned outage because you're updating code, and so you want your roles to recycle and get that new disk that we saw move from E to F and pick up the new code changes. The other type of planned outage is our monthly servicing. So we do it about once a month around, you can guess what time of month. It's our favorite time of the month. Every IT person's favorite time of the month, right? There's a bag of goodies, right? Second Tuesday, bag of goodies comes out from Redmond and keeps you all busy for a while. But so we have to update our data centers as well at that same interval. When we do an update, a planned update of the data center or of your service, we honor update domains. So if you've got 5 update domains and you've got 5 instances, what that has said is we're only going to take down one of them at a time. We promise you that we will not take down more than one at a time. When we're servicing the servers, we can only take down one of those update domains at a time, which means, by definition, we've got to spread those roles across 5 different servers. So that's one of the constraints I mentioned when it comes to placement, the fabric. If you've got 5 update domains and 5 instances, your VMs are across 5 servers now so that we can update the servers without taking down more than one update domain. And our SLA, then, is based on this with you. We've got a 99.95% SLA, and I think I mentioned this, too, a couple days ago, that our SLA is actually very precise. We say 99.95% uptime, availability, over the trailing month to your front ends of a 2-instance cloud service. The reason there's 2 instances is so that if there's a planned outage, there's still one VM up to make your service available. Very different from Amazon's SLA, which says there's a 99.95% chance that your region will be available. So it doesn't talk about your service, it doesn't talk about your servers, it doesn't talk about even availability zone, it just talks about regions. We're talking about your servers. So here's a walking of an update domain for an in-place update. Update 1, update 2, and we do this march based on the health, too. So we wait for those instances to report they're ready, move on to the next one. So the load balancer then can pick those up. Now here's a little tip. If you can, make any configuration changes, push them all into service.cfg. Because config updates are dramatically faster than code updates, just by virtue of the fact alone that we're not copying around role VHDs and creating new virtual disks on the VMs for them, and we're not shutting down your role. In fact, if you respond to role configuration changes, we don't even recycle your role process. So the fastest way to get an update is to get it through code configuration in service.cfg, and then have a role environment changing callback there that responds that you can accept the notification. So your service dynamically responds to configuration updates. And this will take a few seconds versus the marching of update domains for code configuration, for code updates, where we're deploying packages, creating VMs, shutting down the roles, and so on. That can take, on average, 5 minutes. We're bringing that time down. Our goal is 2 minutes, but right now it's around 5 minutes for a couple instance service. Let's talk about maintaining service health now. Now, I mentioned that one of the roles of the Fabric Controller is the health of your services. Its whole point in life in an operating system is serve your applications. And one of the primary goals of serving your application is making sure that we keep you healthy. So there's timeouts and retries and health pings all over the system to try to detect problems, and then automated recovery for those problems. For example, if your role instance crashes, like I said, the guest agent will restart it. If the guest agent itself crashes, which you could actually crash it yourself, you can go kill it, then the host agent's going to lose contact with it, and after a while, it's going to restart the VM, reboot it. If the host OS crashes, so the server has a problem, the Fabric controller is monitoring that, and after a while, it will go and try to fix that server, and if it can't fix it, mark it into what that state called HI, Human Investigate, that you saw in the Fabric viewer, which tells a human to go look at what's going on with that server. And we also have hardware diagnostics. We have we check for smart errors on server boots. We check to make sure that the hardware configuration of the server as we query it matches what datacenter.xml said it should be. How many disks does this thing have? How much RAM does it have? If there's a mismatch, that server is sick and we need to take it out of rotation. Here's just a slide that shows you some of the timeouts. So load balancers pinging, that's part of the health. We're not going to send traffic to an unhealthy role instance. Miss 2 load balancer probes by default, and we stop sending. So after about 30 seconds, we shut off traffic. And then the guest agent, heartbeat, 10 minutes, but it's pinging you every 5 seconds. If you're role entry point, you can see that health probe comes about every 5 seconds. If you miss 10 minutes of those, then we consider you unhealthy, and we'll move your state to unhealthy. We don't actually do anything at that point. It's kind of informational for you because we're not sure really if it's a meaningful state for your application, and we don't want to be premature and recycle you. Fault domains are another way that we take advantage of the hardware topology to try to keep your service healthy. I mentioned that you get 2 fault domains by default, and that means that we spread you across at least 2 racks. And you saw branding police. Those roles were on 2 different racks with 2 different servers. The fault domain is defined by a rack today because of that top-of-rack router. It is a single point of failure besides the server. If that thing fails, we lose contact with everything in that rack, and then we need to move those VMs to a new rack, to servers on new racks. That process is called service healing. It's done automatically. It's done automatically even for virtual machines, for the persistent virtual machine. If there's a IaaS VM on a server, that server fails, or the rack fails, we use the PDU to shut down that server forcefully, so we don't have 2 instances that think that they're both the same thing at the same time. And then we move that VM and recreate it on another server, connecting it back with its blob store. So from the perspective of an IaaS VM, it's as if you rebooted. You had a crash. It'll say system shut down unexpectedly. From the perspective of a PaaS role that happens to, it starts with the wiped memory. It's like it's reincarnated, remembers nothing about its past, which is good because getting killed is a traumatic experience. So, and the OS VHD, differencing VHD is completely zeroed. So it starts completely new. And this is where the 99.95% SLA comes from, because we will tolerate server failure or rack failure and still keep your application alive. So, for example, that rack fails, you can see that we still have a front end and 2 back ends available. Let's take a look at, what happens when service healing happens. Like I said, I've already kind of walked through that. We shut down the server, and we move the thing to a different server. And I actually, just as a little experiment for you, have done that. Let me find I already found branding police here. In this test cluster, you can see that it's here. Wait, is that? Oops. Let me go grab its. Am I in the right? Oh, I'm in the wrong VM. Sorry. I need to be here. So here's the branding police app. Now, what I did is I ran a little command line because they've given me superpowers over this test cluster, so I can do things like this command right here. It's one of my favorite. I'm trying to zoom in. Actually, let me zoom. Let me abort that. Abort. And zoom in on the local system, which will be a lot faster. So there's my favorite command. Force node state, blade ID, human investigate. So even if there's other people on that server, boom. So it's kind of fun. So what that does is this triggers a service healing for the Fabric control. Fabric control says, oop, server's in a bad state. I need to move those VMs off. And here's two snapshots of the cluster. The one we're looking at here, then I HI'd that node down here. Here you can see it again. Boom. So you can see there was actually two other guys on there. Oh, well. And then we all moved up there, it looks like, to that one. So that's service healing in action. And this slide just shows you the same thing. Just the node goes bad and we moved it, reprogrammed the dip. When it comes to updating the data center, this slide really shows you that, remember again I mentioned that we're never going to take down more than one update domain at a time. That's actually an interesting computer science bin packing problem with constraints on it that are kind of unique to Azure and this concept of update domains. So we've worked closely with MSR to come up with an algorithm to do placement so that we can update the data centers as quickly as possible by not creating conflicts between update domains of the same service. And this just shows you an allocation that's bad on the top and allocation, or good on the top and allocation that's bad on the bottom. On the top, we can update those two servers at the same time because we're not violating anybody's update domains. And on the bottom, we can't. We got to do one by one. So that's what we want to avoid. But that, length makes the time that takes to update this data center longer. Here's a tip. This has to do with availability. Now, our SLA with you is that you have at least 2 instances. You notice that we don't have 2 instances of the Fabric controller. Well, one reason we don't is because it's a stateful service. So we need quorum, which means at least 3 for voting. But we don't just have 3. We have more. We have 5. I make the same recommendation to you. If you've got a service that you want to be highly available, don't use 2 instances, use 3. Because your availability is impacted when you're updating your code, so you're marching through update domains, when you're being service healed because the server failed underneath an instance, or when we're updating the host OS or the guest OS. So your availability is impacted when one of those events happens. What happens when 2 of those events happen at the same time? Well, then you're kind of out of luck if you just have 2. So you can take a look at this. We're updating the front end and the back middle tier, one of those update domains with code. So those 2 guys are down for an update. And now, boom, that rack fails. Look what just happened. We've got no front ends available, but we do have one back end, one middle tier available because we had 3 instead of 2. So tip on high availability services to go for more than 2. Now, this last 10 minutes, I want to take you behind the scenes again of what happened on that fateful day back in February, the day we kind of like to forget, the day that Microsoft seems to keep reliving over and over. I don't know if you remember the Zune thing. Anybody have a Zune when that happened? The Zune thing, this was the brown brick Zune, and on February 29th, I guess that was 4 years ago, the Zune wouldn't boot because it had a leap day problem in it. And after a few hours, I didn't even know if Twitter existed then, but everybody started talking about it on the web. And Microsoft support looks at it and says, huh, interesting. Yeah, it's nothing we can really fix. Like, these things are bricks right now. But you know what? It'll go away. So in Azure, when this happened, we couldn't say, oh, it'll go away. Our customers would have said, like, what the hell are you doing with our cloud services? Waiting 24 hours for the problem just to fix itself isn't acceptable. So here's the bug. This line of code was used in a certain place that I'll explain that triggered the whole thing. I wonder, anybody write a line of code like this? Ever? Come on, somebody? Yeah, I can't believe you raised your hand. So what I'm going to talk about to explain what happened here is I'm going to take you behind our operations center and how it operates on a normal day, and then talk about our DevOps on-call model, then talk about what happened, and it highlights the cluster fault isolation, the service healing concepts we've talked about, and I'll conclude with the lessons we learned. So first of all, here's our DevOps center, our network operations center. We have 2 of them. This is the one in Redmond. This is actually 2 doors down from my office. So a couple days before I came here, I walked in there and I surprised them and I said, hey, I want you to do a little video tour for me for TechEd. And they said, do we have a choice? And I said, no. And so they said, okay, I guess we'll do it.
Hi, my name is Julian Gonzalez. I'm Operations Manager here at Windows Azure, and this is our operations room. So on the left-hand side, towards the back, those are customer service folks. They're currently working on customer service problems and helping out our customers resolve their issues. On the right.
So that's customer service. That means problems that have already been identified. Customers have called in. So there's 2 guys there working on that.
Right-hand side, we have a deployment team, and they're currently working on some deployments. We deployed 24/7, almost 365 days a year, except for a couple of holidays. And on this side, we have our build-out team. Say hi.
But that deployment team was over here in the far front right. These are the build-out team. They're really excited to be on camera.
And they currently are working on our build-outs. Technically not operations, live-site operations, because they're building out new clusters every day, and before they're actually in a go-live state, but they sit in here as well, and building quite a few as the demand is high. And then on the right here, we have on this table, we have our live-site operations. There's Robin and Bisme.
Okay.
And
they're really excited too. But notice that the scale we're operating at is hundreds of thousands of servers. Those are the 2 guys monitoring the whole thing.
They perform our live site operations.
And that's a good thing, by the way. It's not like you see none of them. They're not even typing. They're kind of bored. I think one of them's playing solitaire over there.
So that would be your typical live site operations team, and we do. These 2 guys are supporting all of our clusters across all the data centers worldwide.
Yeah, okay. So he's going to talk about what's on those heads-up displays. I'll skip that. But that's the one in Redmond. We've got another one in India. So we've got there's a handoff process, morning and evening when we switch over. When there's an incident that those live site guys can't, those 2 guys in the front right, when there's problems that, of course, that we are aware of, and what we create for some of those are TSGs, or ticket service requests, or I can't remember what it stands for, TSGs. But what they do is they follow certain steps. It says, when this state of this server goes to like this, or the load balancer goes like this, then go perform this script and poke this and peek that. And those are temporary holds until we have fixes in the code to deal with those in an automated way. So that's really what they spend the time doing, is just sitting there monitoring, and then when they see something like that, following the TSG. When they see something where there's no TSG, that's an something unusual is occurring, and let's call somebody. And so this is what's the on-call list for the Fabric team. Every service team has its own on-call list. So the lifesite guys try to figure out, is this a Fabric issue, is it a storage issue, and then calls the on-call. And you can see there's 3 guys there. These 24-hour shifts have to carry around cell phones to be called at a moment's notice. Primary, secondary, backup. Well, that's 4 guys, backup 1 and backup 2. And they really love doing that job. Something I don't have to do, fortunately. Now talk about benefit of being a technical fellow, I guess. But the leap day outage day, leap day thing. So 4 p.m. Pacific is midnight GMT, and that's when the problem started. Let's talk about what happened. So first, we need to understand starting a healthy VM. This is basically a review of what I talked about. The VM boots, the guest agent comes up, and it creates a certificate with the private key, public key pair, passing the public key to the host agent so that they can have a secure conversation over that TCP connection that I showed you in Process Explorer between the guest and the host. Sends over the public key, and then the VM comes up into a ready state, and everything's good. With the leap day bug, the VM came up, the guest agent tries to create the cert, and it fails. And why did it fail to create the cert? That line of code that I showed you, because the cert expiration date was set to current year plus 1. Month and day stay the same. There's no February 29th, 2013. So when it calls create certificate, it gets back an error. Now, the guy that wrote the guest agent, he's so confident in his own abilities that it's like, there should be no errors. And so what it does is just drops the error on the floor, and the guest agent then never ends up passing a certificate to the host agent. There's a 15-minute timeout. No, 25-minute timeout. If the host agent doesn't detect anything, then let's restart that container and see if it works this time. And it tries it 3 times. So, at that point, the whole server is marked as bad, because it's got to be a hardware problem. That's the idea. So yeah, it can't be the software. We're so good. It's got to be hardware. So the whole server gets moved into that HI state. Now, when the HI state happens, you see that we've got 2 VMs there that are running, that are healthy. They're actually in a kind of sick mode, because the only times the guest agent is created is when the VM is created for the first time, or when the certificate expires, after that year. So if a VM is chugging along on leap day, it's unaffected by this. It's only when a VM gets created. But what happens when a node goes HI? We have to evacuate the server and start those VMs on a different server. So leap day starts. That's one HI, just to show that there's one server in HI node. So 3 VMs go, or those VMs go bad. After 75 minutes, those nodes HI. Service healing, 75 minutes later. And yeah, we've got our own virus called the Azure Leap Day virus. And fortunately, we've got a threshold for things like this, where we say things seem to be going out of control. Let's stop, freeze. 60 VMs inside of a cluster of 1,000 go bad, and we basically shut down the cluster. It moves itself into a human investigate state, meaning that service management's turned off. It's waiting for some human to come and look at what's going on and fix it. And in that meantime, you can't deploy services to it. You can't query the status of your services. Though note on this slide that not everybody's impacted. There's 3 customers, purple, black, and light blue. And you can see the purple guy, well, the top guy, complete availability lost. He's on 2 servers that got HI'd, his instances. Customer 2, the blue guy, half of his stuff's on a server that went bad, half of his stuff's still running. So he's partial. And customer 3 doesn't even care. Everything's fine. So different people impacted in different ways. So what do we do? After 75 minutes, that's when the alarms go off in that network operations room. Things all start flashing red. What the hell is going on? No TSG. We're hitting service cluster HI threshold 60. Service management's turned off on a whole bunch of clusters. What makes things worse is that we were in the middle of rolling out a host OS update. And when you roll out a host OS update, we were rolling out a guest OS update at the same time, which means that the VMs are getting restarted on those nodes as we do the updates of the cluster. So we were actually promoting the virus through our updates. So what we decided to do, we had these partially updated clusters and fully updated clusters. For the fully updated ones, we said, let's just push out the new fix in the normal way. So it just gets rolled out across the cluster. For the non-updated ones, we said, which had just started their updates, we said, we could either let them finish what they're doing, which is going to take hours because of the monitoring update domains, or we can just roll it back and start over. And that would be faster. So we'll just roll it back to the previous version and see what happens. So fixing the updated clusters, what happens is we produce a new package for 119 version of the host agent networking plugin and host OS. And we deploy that. Restart the machine. Everything's green. Restart the machines. Everything's green. Now we have to update the guest agent. because the host agent and the guest agent both have this certificate problem. And then we're green. Now, for the partially updated ones, here's what we did. We're going to roll it back to 118 completely, because you can see we got 118, 118, 119 over here on the far right. Let's just roll it back to 118. You see something wrong with that package? We wanted to roll the whole thing back to 118. Somebody forgot to put in the 118 network agent. The 119 network agent is incompatible with the 118 host agent. So, bad things happen. So the VM starts, the host comes up, but it can't talk to anybody because the network agent is broken. So that guy on the far right that was doing fine, now he's in trouble. So most of the clusters were completely repaired because they've been fully updated. 7 clusters were left in this weird state. This is at 3 in the morning at this point. People have been on this for 12 hours. And so bad decisions are made, like that rolling back versus rolling forward. So what they decided to do, I wasn't actually in the room at the time, this is like 5 in the morning. They said, okay, how do we fix these 7 clusters? So they took the 119 agent. These machines are basically, clusters are completely offline. Normally we do this nice rollout. So what they decided to do was a blast update. The problem was we couldn't even do so they did a blast update for these, and those went green, or they're supposed to be green. But there were a few clusters that were completely hosed so bad that automatic updating was off, and we had to manually roll out the package. So people had to sit there with FC Client and custom scripts that we were writing 6 in the morning, 7 in the morning, 8 in the morning, one by one to update these things, which took hours and hours and hours. But eventually, we got everything working. So we took these lessons to heart. This was a very painful experience for us and painful for our customers. A couple things. One, time can be a single point of failure. Who would have thought? And this is kind of an interesting dilemma. How do you defend against a leap day kind of bug? It's really hard to. Because if your old code has it, there's really no way to avoid a kind of cascading failure of that. Really, the only solution is to fix it as quickly as possible. So having a quick recovery process is critical, we obviously discovered. Cascading failures can be a side effect of even recovery. As we saw, the service healing actually forced this problem to spread. We needed a safe mode for all services. When the clusters were HI'd, then nobody could even query the status of the service. So you could see your service, you could go to, hit the front end of it, see that it was there, but you couldn't call the service management APIs. So we want to have a read-only mode. Recovery needs to be a normal path, not people writing scripts at 7 in the morning to fix things because they need sleep, and the customer needs to know what's going on. So the bottom line is that we initiated something called a dial tone effort, where we said, let's go and systematically look at our whole system to make sure we don't have other vulnerabilities like this, that we have fast recovery, that we've got fast rollback, that we've got automated recovery every place. And we actually ended up doing something called failure mode analysis, which is tracking dependencies and what happens if this fails, what's the impact on the things that depend on it, and do they recover from that in a graceful way. And that's going to be an ongoing thing, but we've made a lot of progress already in cleaning up some stuff that should have been fixed, like what just happened right there. We also know that we need to be more proactive about what's going on. There's a blog post, actually, that describes exactly what I just showed you that we published about 10 days afterwards in gory detail, exactly like I showed you, to just be open about, hey, we screwed up, but we're learning from it, and this is exactly what happened. And this, I want to leave you with this, because this is our ultimate aspiration, where the fabric controller is in charge of its own destiny. Actually, there was an article that came out yesterday that said, in these large systems, there's signs of machine learning, spontaneous machine learning going on. Well, we hope to build something where the LifeSite guys, there's just one of them. Actually, there should be always two, like a co-pilot, I guess, in case the first one dozes off or something. But But humans are bad. That's another lesson that we learned. So with that, I want to leave you. I hope you found this kind of interesting, kind of from a geek perspective of how we're operating at scales of hundreds of thousands. Also, I hope that it gives you some insight into what happens when you're deploying your service or when something happens in the data center, what steps we're taking to recover from it, how to maximize performance of your services, a few tips along the way. And with that, I want to wish you a great TechEd. I hope to see you at my session this afternoon in this very room. I'll be doing malware hunting with the sysinternals tools. Casey then explained tomorrow afternoon. Please fill out an eval and have a great rest of your time here in Amsterdam. Thank you very much.